and we can get started. Are there any questions so far about things in the course, even if there are any questions about the midterms or something? Okay, I take that as a no. In which case, let's get started. And now that the midterm is over, we're starting a new block, right? So we're more or less roughly now in the third block. The first block was really developing the very basic, field equations for the electromagnetic fields, which basically led us to the Maxwell's equations. And the second block was then, well, can we find solutions to these field equations? In particular, we looked at them in the context of the Laplace equation mainly, but also in terms of the method of images and also multiple expansion. So we gave you several ways um, to solve them, which go a little bit beyond what you've kind of seen more or less 2041, where you have to rely on very simple integrals and symmetries in order to perform the integrals. So what we're going to do in this block is we're going to increase the complexity a little bit more, in particular by moving away from vacuum or even very simple conductors. Okay, and so we're going to consider materials, and in particular we're gonna take a look at how do these equations change if I consider something that moves away from the regular vacuum. And so I want to just start by recapping some of the things that you should know. So we're going to talk about conductors first, but we're going to soon move on to something called dielectrics, insulators. And so the first thing that I want to pose, and this is something that you ought to have seen in 2041, is asking the question, what is the difference? So the question is, what is the difference between, let's say, one, the conductors, and two, insulators? Okay, so let's take a minute or two to remind ourselves, to refresh what are really the differences macroscopically between conductors and insulators. So, any ideas? What is the macroscopic, or what is the behavioral difference between conductors and insulators? Anybody? Everyone is still stressing about their upcoming midterms. Oh, okay. Okay, so Alex is saying conductors have higher conductance, but insulators have lower. Not long is saying electrons move freely. So both answers are correct. Right? So conductors pretty much by definition have higher conductance, whereas insulators it's lower. The underlying structure or the reason why this is, that's what Maklov is saying, this is the electrons move freely. So indeed, um, what we typically say is that it's the motion of the charges um, due to the external electric field. So we're going to consider magnetic fields later on. So here we're going to first take a look at electric fields. And so indeed, their difference is, inside the material, are there any charges that can move freely? So for conductors, we have basically, moving charges, or even altogether freely moving charges. And for insulators, we have pretty much non-moving charges. And this difference actually gives them a very different properties if you look at their if you look at their kind of behavior in an external electric field. So for example, for conductors, okay, so for conductors, we know that we know that charges move due to external electric field. Okay, and so this actually has a consequence that the electric field inside must be zero. Because if there was a non-zero field inside, there'd be a current, right? If there's charges can move freely, there's a field, and so the charges will, there's a current, the charges will move, and so there's going to be energy dissipated, and there's no way to to sustain it, and so the charges will rearrange themselves in order to achieve an equilibrium. And typically the equilibrium is when the fields are cancelled. Okay, so we can take a look at an example in this case, where we take some slab, okay, of a conducting conducting material, and we place it in some E field here, and this is the external E field. And so what's going to happen? Well, what happens to charges when there is an external E field? Well, the positive charges are going to be are going to be moving, and the negative charges are going to be moving. Okay, or in this case, since we're only dealing with electrons inside materials, the electrons are going to be shifting, and so in such a way that the inside of the field must be the inside of the material must be zero. So in this case, what we're going to see is that there's going to be negative charges piled up here, and then in such a way that there's a net positive charge on the right side. And of course, in this case, it is the electrons that move. There are no positrons that can go around, but the net effect, nevertheless, is that there's an electron over density on one side and then an electron under density on the other side, in such a way that we can create, a positive and a negative field. And so we know from the properties that then there's an internal field, E field, EI here, in such a way that EI, okay, is the same as E external, or the original external field, in such a way that the total electric field, which is just E plus EI, equals to 0. Okay, and so of course we then know that if I take the divergence equals rho epsilon naught, but in this case the total field equals to 0, and so here we must have that rho equals to 0 inside. Okay, so as I've drawn here, and on this in this picture here, we can more or less speculate where the charges are. Right? In this case, because it's a slab, it's a little bit easier to consider because we've got an E field that is that goes along this slab, and so it's easy to see, okay, well, where's the charges, or at least the over densities, where are they going? But we can actually make this a little bit more formal, in such a way that we can show. Okay? So we're still talking about conductors, so we can show that charges, okay, must be located on the surface. On the surface. Okay. Now, of course, in this case, we know, because if there's any charge inside, then we have a non-zero electric field. Okay. And the charges distribute themselves, right? So distribution will cancel the inside and outside fields. And we can actually make this, we can make this argument explicit, okay? And we can actually consider the energetics that is needed for this. So, what we want to show is that, energetically, we expect the charges to reside on the surface rather than on the inside the bulk. Okay, and so what we can do is we can consider the following two scenarios. So we can consider, one is here is a spherical shell. And we can consider just a solid sphere. Okay, now we can associate each charge, each of them to have a total charge Q. And then we can see, okay, well, where is, what are the energetics associated with this? So the first thing what we want to do is we can evaluate the energy as simply 1/2 of the charge density. In this case, we place them on the surface, V dA, where V is now the potential. And so in this case, let me make sure that this is divided. It's a bit easier to see. Okay, so in this case, what is the electric field you know, inside and outside of the spherical shell? Well, inside is 0, right? There's no excuse me, there's no charge in there, right? Because we're considering a spherical shell with some R, and outside is just K E Q over R squared in the R direction, and that is for R is bigger or equals to R. Okay, and so what we can see here, V is just the integral from infinity to R E dot dl is just KE, let's see, let's write KE Q over big R. Okay, and so ultimately we know that on the entire surface we have another factor of Q in there in such a way that W here is just a half sigma V dA equals KE Q squared over 2R. Okay, so this is a calculation that you should have seen in 2041, and this is relatively, relatively straightforward application of the integral forms. Now we can do exactly the same thing where we have a sphere with a uniform charge distribution. Okay, so this is uniform rho here. And so here, what we can do, we can make our lives, a little bit simple, and we have that E here. And now what we do is we have KEQ. Well, okay, no, let's do big Q. Let's do big Q. Okay, divided by R squared R hat when R is bigger than big R. So we have the total charge, which is just, we can assume that this is everything that is inside. Of course, if we are not inside, when R is smaller than big R, then we have the proportion that is associated with, small r, and then R hat. Okay, so in this case, what we have to consider is the proportionate amount, because we're not all the way into big R anymore. We have to consider the proportionate amount of charge that is there, and that's how we get this big R cubed, but also just a single R over here. Okay, and this is for R smaller or equal to R. And again, we can consider W, the energy, but now I use a slightly different formula because this is easy. So this is just a half E squared d tau. So just integrating the electric field. Again, if I want to use this formula, we have to go through over all space. And well, we simply do the integral here. And well, I'm going to let you well, I'm going to leave this up to you. It's a relatively simple integral in R itself. If you do it in spherical coordinates in such a way that you get KE big Q 2R and it's 6/5. Okay, and so what we see here, if we look at these two calculations, is that you know, is that if I compare this one here on the left, the answer, to the one here on the right, we see that there's it costs more energy. Right? There's more energy inside a system where the charge is uniformly distributed along a sphere compared to if all the charges are really at the edge. And so even if we have a conductor, even from energetic arguments, you can say that all the charges prefer to be on the edge in such a way that it minimizes the energy inside this configuration. Okay, so excuse me. And so what we have now is a system. If we talk about conductors, is inside there's no charge, only charges if there are any charges, if there's any external fields, or if there's any charged, if it's being charged up to a certain level, they must be on the outside. Okay, I think this is a good time to take a quick break. Let's take a 5-minute break before we come back. So we come back at 5:03. Okay, see everybody in a minute. Okay, welcome back. Let's dive straight back into it. Um, and so we just talked a little bit about conductors, and in particular that the electric field is zero inside, and so all the surface, all the charges that must reside in there must be on the surface. Similarly, if there's an external field, the redistribution of charges must be on the surface as well. We saw that from an energetic argument. And so when we talk about problems involving conductors, it's actually relatively simple because we know the inside field equals to zero, and then the only thing that we need to consider is what happens outside the conductor. And so here, what we're considering is what we need to consider is to, we need to determine the field in the outside material. In this case, it's either vacuum, in which case we have that the divergence equals to zero, and of course we have that the curl. Okay, I'm gonna stop writing the curl as that. Okay, E equals to zero, in which case we simply have the Laplace equation to solve. Okay, and so we've kind of seen this in several occasions, including even on the in the midterm where we imposed some charge distribution on a particular surface. Or we have insulators, and so, but in the remainder, we're typically going to refer to this to dielectrics. And this is the thing that we'll talk about, momentarily. So we basically have these two situations, right? So if the conductor, we know exactly what happens in the conductor, and then we need to also see, what is the solution to the fields outside. Now, of course, the other thing that we may need to calculate is the actual distribution of charge on the surface. Okay, and for that, what we do is we look at the boundary conditions. Okay, so here we just have to consider the boundary conditions. So let's take a quick look at the boundary conditions for the electric field. And let's see if we can still remember what they are. The electric field. So let me give you a minute or two to refresh yourself. What are the boundary conditions of specifically here the electric field? Okay, anybody? Boundary conditions for the electric field. People still with me? I think the end of term is coming up, or at least we're in the middle. I think people are getting a little bit tired. Okay, here we go. We see some movement. E above minus E below is sigma epsilon, Ricky, and E above E below sigma epsilon E above E below. Okay, okay. So Ricky and Shanti and Alex are giving more or less the same answer. Again, what is important is that we remember that there is a directionality here. So it's important to make these distinctions. Okay? Which direction is the discontinuity, and which direction is it continuous? And so if I indeed draw a surface, like this, and consider indeed the field that goes this, and a field that goes like this. So one is perpendicular, and one is in a direction parallel. Then, as we've seen before, is that the E perpendicular is sigma epsilon naught n hat, where in this case n is the normal to the surface. And so this, of course, equals to E above minus E below. And similarly, the one parallel to the surface equals 0. And again, this is E above minus E parallel below. Okay, so these are generally or generically the boundary conditions for the electric field. Right? Any surface, whatever goes on, these are the boundary conditions. And so we can apply them to conductors here, in which case we know that the below, assuming that the conductor is below, is has the electric field that is 0. So in which case what we simply have is that E perpendicular again is sigma over epsilon naught n hat, which is equals to the the field, right, the gradient dotted with n hat, and sometimes this is written as d phi dn. Okay, and here what we have is that again the one parallel equals to 0. And so when I have found the surface charge, right, or if I want to find the surface charge, then I need to find, I just need to find the solution to the field, to the scalar field in this case. And then I can simply take the gradient in the direction normal to the surface. That then gives me the electric surface charge. Okay, so that's for the for conductors, right? This is a super brief recap of conductors. And what we can do instead is now we can look at dielectrics. So let's consider dielectrics or insulators instead. Okay, and in particular, the you know, we have basically non-moving charges in such a way that there is no constant current flow. In other words, there's no current flow that could redistribute the the charges. So if there is an external field applied to it, you know, it may be able to induce some motion, but not necessarily the currents that are needed to spread everything out. And so the electric field inside is not guaranteed to be zero. Okay, and so the question is, how does the field, interact? The field inside interact with the field outside. And this is a pretty generic question. This is pretty a pretty fundamental question. So what happens if you apply an external electric field? What happens inside the material? So let me give you another 2 minutes to refresh. How does it change if I have a dielectric or if I have an insulator? How do things move about? What happens to the field inside? Okay, give you a minute or two. Okay, so the question is external electric field. We put an insulator in there. What happens? Anyone have any ideas? induced dipole. Sure. So Winglock is saying it could be an induced dipole. Yes, could be. Okay. Now, this is often what happens, right? We see an induced dipole, but the reality is very simple. We don't know. Okay. And yeah, what is important to realize when we talk about dielectrics, insulators, so anything away from perfect conductors, is that we simply don't know. Okay, it simply depends on the properties of the material, and that's really where the challenge lies when we talk about real life material science. Is that we need to be able to specify this. Now, it doesn't mean that we cannot build a more or less a framework to think about and to look at these things. But I wanna stress upon you that this is something that we simply don't know. Okay. Um, you know, Nevertheless, there have been, for example, experiments done to consider, okay, well, what happens if I put what happens in dielectrics. And so the most I wouldn't say famous, but maybe the earliest experiments were done of the following form. So let me consider a capacitor. Okay, so I've got a capacitor like this, and in this case I've got some plus Q, I've got some minus Q. This is V plus and this is V minus. Okay, where V is now the scalar field, and so the complete V is just V plus minus V minus. And so we can define a capacitance by looking at the amount of Q divided by V. Okay, and then of course for completeness, what is the work done, or what's the energetics? It's just V dq, small q, which in this case is just QC dq, so that the total W, when you integrate this, Q over C dq is simply a half big Q over C, sorry, big Q squared over C, or a half CV squared. Okay, so this is what we've seen before. Now, what happens if I now put a material in between? Okay, so instead of vacuum, I put some dielectric. What happens then, generally? Does the capacitance go up or down? In fact, this was actually one of the original experiments by Faraday. Right? He built the capacitor, and then he just put like slabs of insulators. I think it's typically wood. He put them in between, and then he observed. He's trying to see, okay, well, what happens to the capacitance? Capacitance go up, higher capacitance. That's right. And so in that case, if there's a higher capacitance, what has to happen? If I keep the charges the same, okay, so indeed C goes up, what happens to the phi goes down. Very good. Anyway, I'm glad people are participating again. This is the point of being in a live lecture instead of just listening to the recording of this. So indeed, okay, C goes up, B goes down. And so, you know, it's very tempting, and it's very it's very tempting to think about it in a different way. So that, you know, when we talk about the vacuum, we have the you know, we have the epsilon naught, right? It's a constant of proportionality. And when we talk about, you know, the field decreasing, then, you know, it's tempting to think about it in terms of, you know, just redefining the constant. So different materials have different constants associated with it. Okay, so vacuum, epsilon naught. And so instead of thinking about everything in terms of epsilon naught, you know, can we write things in just a simple replacement of the constant of proportionality, depending on the different materials. So the situation tends to be slightly more complex. There are certain cases where indeed this is possible. Okay, so this is sometimes possible, but not always. Okay, so in order to see kind of what's going on, we could take a look at a little bit more detail in what we may consider that is going on. Okay, so the first example I want to give you is a simple hydrogen atom. Okay, so imagine, oops, let's change the color. Okay, now let's take a look at a simple hydrogen atom. Right here, and there is some, you know, thing in the center, and here is, and so here we've got the cloud, which is typically an electron cloud, and then here at the center is my positive nucleus. And so when I put all of this in some electric field, so now what I'm going to do is I'm going to put all of this in some electric field. Oops. Put all of this in an electric field here. This here. Okay. So now I've got some external electric field. And so what do we expect that is going to happen? Well, in this case, we know that it's typically the electron cloud that gets to move, and then of course the positive nucleus, you know, because it's much heavier, doesn't move. But nevertheless, what we can do is simply, you know, draw the situation in such a way that we have, this is the old center, and now we have that the positive nucleus has moved with respect to the electron cloud. So again, in blue we still have the electron cloud, but now we have the positive nucleus has moved. So let's see if we can analyze this situation, and let's see if we can, you know, we can somehow, you know, see what's going on in terms of the fields. So if I take a look at the left hand situation, then, you know, I could first say that the E field inside is simply KE Q divided by big R cubed R. So here I'm just talking about the magnitude. So if I'm inside this cloud, right, which we can consider to be the same as just a conducting sphere where the charge is uniformly distributed. And so I get a scaling that goes like this over here. Now, if I indeed now use this and analyze this scenario where, let me give this separation, let's call this D, then what is the electric field between the two things? Well, in this case, this is E is now KEQD, right? That's a separation R divided by R cubed. Okay, again, it's a little hand wavy. It's okay. Don't worry about the precise nature, but what I do want you to see here is that we get this factor here, which is Q times D, which, as we've seen before when we looked at dipoles, right, in a multiple expansion, that we can say that it's just P is some Q times D. Right? And so if we assume that everything is more or less constant and kind of in this toy picture, then we can actually write that P is QD, which is the same as E R cubed divided by KE. Okay, just by rearranging this equation over here. But of course, R cubed over KE is just a constant. So we can have alpha E, where in this case, alpha is just R cubed over KE. Okay, and so we can already start noticing that if we indeed put some external electric field in this system, then we're inducing a dipole moment. Right? There's this P, just Q times D, that depends on the external electric field. And so we can actually take a look at this in a little bit more detail. So indeed, this is actually called the polarizability. Polarizability. I hope I spelled that correctly. Okay, so typically what we have is so the induced dipole moment is related to external field. For example, P equals alpha E. Okay. And typically it's better to write P as a vector quantity E alpha, like this. Okay, now alpha could be well, in the simplest form, alpha is a constant. Okay, but it doesn't actually need to be, because in general, the polarizability is can actually be written as in the following form. Can be written as P equals alpha, where now alpha is a rank 2 tensor. Again, we're not going to go into details about what this exactly means and the details of second rank tensors, But what we can say is that we can write P of x. So the x component is just alpha x x e x plus alpha x y e y plus alpha x z e z. Okay, so in a way, instead of it being a constant, where the induced dipole moment is in the same direction as E, as the external field, but here what we can do in general is have it point in any direction depending on this alpha, which in this case alpha is a second rank tensor. So again, Py is just alpha y x e x plus alpha y y e y plus alpha y z e z. Okay, so you get a mixture between all the different components of the electric field that then go into just the x direction of px. Okay, now how could this be like why could something like this happen? And in order to maybe make that a little bit more plausible, we could also look at a specific example, where we look at molecules instead. Okay, so in the very simple example that I've shown here, in this case, this is a neutral hydrogen atom. There is an external field. Everything is being dragged along, and we get something where P is in the same direction as E. Now that doesn't necessarily need to be true, and so in order to make that a little bit more plausible, what we can do is consider a slightly more complicated molecule. So in this case, let's consider a different molecule. Let's consider water. So I've got O, H, H. Okay. So in this case, these are the H, hydrogen, and then oxygen. And for those who are interested, this angle, does anyone remember what the angle is? Do we still remember our chemistry from year 1 and year 2? 109, 105, 104.5. Wow, okay. You guys remember it much better than I did. Okay, somewhere between 100 and 110. Okay, that's the extent to which I remember it as well. So at least the number that I looked up was indeed 104.5 degrees, but it doesn't really matter. Okay, now what is important in a hydrogen atom, in a water molecule, is that you actually get a polarization, a natural polarization. So we get that the plus density is distributed along the hydrogen atom, and then there's a negative, charge distribution around the oxygen. That actually makes why water is such a good good solvent, right? Because the water molecule can rotate, either the positive side or the negative sides to compensate. Okay, so now what we have is indeed something that pretty much naturally look like a dipole, right? Indeed, we have something that looks more or less like a dipole. So what happens if I have something that has a particular dipole moment? What happens now if I put this in a field? Well, let's take a look. So if I have something like this, where this is now, where this is now a, let's make this plus Q, and here is a minus Q. Okay, so this is my dipole moment, and let's make this the middle here. Let's make this R plus, R minus. Okay, but now I'm going to put in some external electric field, E. So without going into the details first, what's going to happen to this molecule if there's some external field? Okay, Alex is saying rotate. Okay, why? Can you answer the follow-up part? You know, why would it rotate? Okay, yeah, that's from an energetic argument. So Alex is saying the configuration of rotation, rotating the dipole 90 degrees clockwise is more energetically stable. Sure, yeah, absolutely. You know, we can analyze this a little bit more at a slightly lower level. So here, oops, try a different color. A net torque, indeed. So that's exactly what Harry is saying, right? So there is a net torque in this system. So let's see if we can draw this out. Okay, I don't know why I keep forgetting to make this green. Green. Here we go. So indeed, there's one here and there's one here. And so in this case, we've got a positive charge, so we've got some net force here, F plus. We've got some negative force here, F minus. And you know, and so what we can do is we can now consider F plus is QE, F minus is minus QE. Okay, let's give this a little bit. Give each other this one, and then there is the net torque. Indeed, is given by N. Is just R plus F plus plus R minus F minus, like this. Okay, so let's take a quick look at what we get. Well, this is just a half D. If I make this entire thing D, give it an arrow as well, cross Q E plus minus a half D. Again, there's a directionality. If I make the center point the origin, cross, in this case, minus QE. Okay, the two minuses drop out. And so what do we have? Since Q is just a constant, I can take that out. The first term and the second term are the same thing because the minus signs here drop. And so I get Q D cross E, which case is just P cross E. Okay, so there is indeed a net torque that is associated with the existence of some naturally occurring dipole moment. So here we can see that there's a rotation that occurs in the system if I apply an external field. And so one particular scenario could be that since these water molecules are all randomly distributed, so their dipole moments are are completely randomly orientated. And as soon as I flip on the external electric field, I'm aligning all of these dipole moments. You know, because of the torque, I'm aligning them, and so the whole system gains some net, uh, gains some net dipole moment. Right? So even though if you look from very large or far outside, you don't see a net dipole moment because all of these water molecules are randomly distributed. But as soon as you turn on the E field, you get the alignment, and then you get a net dipole moment that is non-zero. So that's another way in which we can obtain it. And starting from this picture here, I want to, I think it's easier to see how you can actually get something that is not where alpha, where the polarizability is not proportional to E, not necessarily proportional to E. Because, again, this is a water molecule and we looked at a hydrogen molecule, but most materials, or at least some materials, consist in terms of crystals. Right? So the structure in which the molecules are organized, or the atoms are organized, is according to a very tight lattice. Okay. Now the reason why that happens is something that is beyond the scope of this lecture course. That's something that you'll need to go into statistical mechanics to get into the details. But nevertheless, there's a lattice structure that exists, and which is very difficult to break, right? These crystal structures. And so, depending on the orientation of these crystal lattices, you're actually getting, some degree to which you can move things around or not, depending on the orientation with respect to the crystal lattice. And so, even though I've given you two examples where you'd expect that the alignment is exactly in the direction or not, but hopefully from at least the molecule perspective, once they have to follow some certain crystalline structure, it is no longer necessarily the case that whatever external field I apply, I get the same, I get a dipole moment exactly in the same direction. Okay, so that is indeed important to realize, to consider. And so what I want to do next is, now that I've given you some examples, I want to delve down a little bit into the mathematics. Okay, so what does all of this mean for our scalar field? Okay, which is what we're interested in. So let's do that after a quick break. So let's come back in about 5 minutes. So we'll come back at 5:53, and then we'll look at a little bit from a mathematics perspective what happens when in those cases. Okay, see everybody. Okay, welcome back. Let's do this last stretch of the lecture, and let's indeed look at the specific example of what happens to the fields. And so, what I want to do is set up the following situation. So let's consider the scales. Scalar field. Okay, so let's set up the following. We're going to set up a coordinate system. Let's do something like this. Let's call this X, Y, and Z. And now I've got some material, and I am considering a particular point here. So typically what we call this is, for the material inside, is R prime. Then of course I have different colors. I have the location where I am evaluating my potential. And now I'm going to add one little thing here, because what I want to do is I want to consider individual units. Typically, we can say molecules or kind of crystal groups, but I want to be able to do that as well. So let me define this region here, this, and then I have another vector that then spans like this, another tiny vector here, which is just R double prime. And the reason why I want to do this is I want to account for some of the finite sizeness of the molecule or the crystal, the periodic crystal sites. So I've got three different scales. Ultimately, of course, what I want is to evaluate what is the influence of from here all the way to here. Okay, and so in this case, what I'm still interested in is to consider this. Well, okay. Okay. The reason, what I want to consider is the following. Is now, because we have the field of R equals KE integral, this is what we've seen before, R minus R prime dV prime. Okay, so here instead, what I want to do is I want to now, because I've got three scales, I'm actually gonna consider 1 over R minus R prime minus R double prime. Okay, now don't be alarmed too much. The extra scales are gonna drop out very soon, but I want to start off with these three different scales. Okay, now the first thing that we've done before is when we looked at the multiple expansions, say, okay, well, I wanna only keep some leading contributions. And so in this case here, what I want to do is I want to do an expansion where I group these together, and this is basically my small parameter. Now, before I continue, even in this expression over here, I wanna see if you remember the multiple expansion. Okay, so this R minus R prime, 1 over R minus R prime. What is the multiple expansion of this? Okay, I'll give you 2 minutes to think about, or to remind yourself, refresh yourself, or even just look it up. Okay, let's go. Who's the first one who's going to give me an answer? Very good. Pearl, Harry. I still have no idea you can write all these symbols in plain ASCII, but very good. Okay, so indeed we see here a sum of Legendre polynomials and an expansion in R prime over R. Very good. Okay, now I've also shown in the lectures that you can write this as a kind of as kind of dot products instead. And so if I write it in that form, then it would be something that looks like this: 1 over R, 1 plus R hat dot R prime divided by R plus, in this case, it is 1 over 2R squared 3R hat dot R prime squared minus R prime squared plus dot dot dot. Okay, so actually let me rearrange this. It's less awkward. Okay, let's put this here. Let's put this here. You gotta love modern technology. Okay, so I can do the same thing now with this expression that I have below here, but instead now we're gonna take our double prime to be the small one, and so I can write this as R minus R prime J plus R minus R prime J, and I'll show exactly where the J comes from, because the J here, oops, the J is here to denote which element I'm considering. Okay, so in this case, I have to keep a J around, just in order to be able to vary among all the different molecules or the different sites. Okay. Make this blue. Okay, this dotted with R double prime J divided by, now I've got R minus R J cubed, and then plus, and the other extra expression. Okay, so here I've simply put the R inside, and instead of a hat, I've added another factor of R here. So indeed, this becomes R squared, and if you take R here instead of R hat, there's a third one coming here, which is this one. Oh, sorry, you don't see the mouse. So I've got here, I've got R, and instead of making this a hat, I just make this a regular R, and so there'd be another R here. So that's why there's an R cubed here. Okay, and again, we're expanding over the double prime, so I leave R minus R prime over here. And the label J again is just this site. So this is the J site. Okay. Okay, so I've only kept it to the leading order because that's pretty much going to be enough. And so what if I now look at phi, which is my scalar field, as a function of R? Well, that would be Ke, and it's the sum of all the different molecules, all the different sites, but I'm integrating, okay, this is rho as a function of double prime, right? Because we're only considering the charge density inside my molecule, and now it's divided by R minus r prime j minus r double prime j dv double prime j. Okay, so let's take a look. And now we use this expansion below in order to write ke, the sum j, and I've got 1 over r minus rj integral vj, okay, rho r double prime j dv double prime, okay, don't need the j, plus ke, the sum of j, and now I've got r minus rj over r minus r prime cubed integral of r double prime rho dv. Okay, so these are the first two terms. Here I've got rho double prime. So if I now multiply this here, I rewrite it in this form, then I've got this rho double prime and just the term with rho. So this is actually exactly the same thing as we've done before with the multiple expansion. Right? This is nothing different except for, you know, I've relabeled some of this stuff. Okay, so now in this case, what I want to assume is that the individual molecules themselves, okay, so the sites of molecules are neutral in such a way that the integral of Vj rho r double prime j dv double prime equals to 0, right? Because that would be the charge inside this molecule on a jth side, jth molecule. That what we can do is set that to 0. So then, you know, the next leading order, is the dipole. It's the dipole moment where I just get integral of Vj of r double prime rho r double prime j dvj double prime equals pj. Okay, so this is the dipole moment for the jth atom or molecule. And so in this case, what I can write now is that the potential V as a function of R is just it's just Ke, the sum of all the different molecules, R minus Rj divided by R minus Rj cubed of my Pg. Okay, so this is in principle sufficient, right? So the formula that I've got now is simply adding all the contributions, all the different dipole moments at every single molecule, right? This is what this says. This is a sum, and here it's a little bit written in a convolved form that only says that, you know, this is the location between my jth molecule or jth crystal site to where I'm considering the, right? So here, all that I've got is, you know, green, the site in green to the site in red. What's the dipole contribution to the scalar field? Okay. Now, one thing that I can do is instead of taking this microscopic picture, right, where I'm taking every individual site separately, I can actually make this. I can turn this into an integral by considering so consider a continuous distribution. Oops. And just do anything. Okay. Don't know why this is. So if I consider, instead of all the different PJs, I consider some density distribution. So in this case, I can call this the polarization density. So I can make all the PJs. Instead, I can make a P R prime J, okay, and then some volume Vj. Okay, where now P is now the polarization density or distribution of the polarization. And if I write everything like this, well, then I can turn this into an integral instead. So now I can turn this, especially when I take delta V to 0. So okay, let me just write it out. V of R is just KE. Yes, density is a vector. Yes, that's correct. And KE, and then I got the sum JR minus RJ divided by R minus RJ. This is prime cubed, and then P R prime J, sorry, delta Vj. And now I can take delta Vj to 0 and the number of molecules to infinity. So we get just a Riemann integral. So here is KE integral of the entire V, P R prime. And now it is still here, I've got R minus RJ over R minus RJ cubed dV J. Okay, sorry, no need for the J anymore. But I do need the prime here. Okay, I'm going to use a slight little trick here where I'm going to rewrite this R minus RJ divided by R minus RJ. I can actually show that I can write this as the gradient of 1 over R minus RJ. So KE V P R this. And now what did I get? I get that this is the same as the gradient of R minus RJ. Sorry, R prime. dV prime. Okay. Now this is actually an identity that you can go and check for yourself, but it's something that is relatively straightforward to prove. Okay, so I've got this now, just a few more lines so that I can rewrite this. So I can write this now as, let's see, KE, and I'm going to rewrite this as the integral of V here, P dot over R minus R prime, like this, and then minus the divergence times 1 over R minus R prime, like this, dV. Okay, so I'm just, this is the same as kind of integration by parts, if you will, or if I just expand this, I get here the divergence, and then here I get the gradient of this. And so this minus this term gives me this term over here. Okay, and we can see that this is the first term. Here we get that this is the, this is a a derivative, in particular a gradient, sorry, a divergence of integrated over all of space. So I can actually use Gauss's theorem to change this into a surface integral. And so here, what I end up with is that phi as a function of r equals to ke, the integral of p as a function of r prime divided by r minus r prime dotted with ds prime, and then minus ke integral, and this is the divergence of p r minus r prime dv prime. And this is exactly where the position that we want to be in, because what we see here is that we have two contributions here. Okay, and we have something that here in green, this here looks to be something along the lines of a of a surface charge density, right? Because this then has to be some charge, right? Because we've got that the scalar potential is just some charge over 1 over r. And this here is an equivalent, isn't it? The divergence depends on the unprimed coordinate, but the integral is in, I'll get to this in a moment. The thing is, when you do this in r minus r prime, you can always flip the divergence from a prime divergence to unprimed divergence if it only depends on 1 over r. If it depends on 1 over r minus r prime. Okay, but I'll get to this. I just want to finish this part first. So here we have we have something that looks like a surface component, and we have something that looks like an actual charge component, right? Because this is just 1 over r minus r prime, and so on the top we should expect something like a charge. So here, we end up with the identification. We get some sigma, which is p like this, dotted with n hat, and some rho p, which is just the minus the divergence of p. Okay, so what does this mean? Okay, this means that we have induced surface and volume charge densities. So just to finish off, just to recap. So if we put an external field, we know we can incite a dipole moment. Again, it doesn't have to be exactly pointing in the same direction as E, but still we can incite, we can incite or induce a dipole moment. And so by just looking at what is the influence of this dipole moment to the external scalar field, we end up with, if there is some charge density, if there is some polarization density around, so if the material is being polarized, then we end up with either a surface contribution, right? So it's an induced surface charge, or a induced volume charge density. And so that's the thing that we tend to see happen. Of course, if you've studied your vector calculus properly, you'll see that you'll know that whether this term goes to zero if P is just a uniform field, uniform vector field. But we'll talk a little bit about this in the next lecture. Okay. But the bottom line, the take-home message is that external E field induces a polarization, and this polarization then comes out as both a surface charge density, and a volume charge density that is given by these two expressions over here. Okay, that closes out for today. Next lecture, we're going to take a look at a little bit more detail, and we're going to take a look at the, if there's time, the magnetic equivalent of this effect. Okay, thank you very much, everybody. And why don't I also now go to Alex's question? So Alex says that the divergence here. So the divergence here is actually, is very versatile here, right? So here, this divergence works both in here and the one in a minus sign. Here, this one is minus the other one. And so depending on whether which you take the divergence to be, then yes, there is a minus sign here that I seem to have missed. Yes, there should be a minus sign here. Let's see. There should be a minus sign here. Okay, I think I dropped minus signs somewhere. Okay, I need to figure out where I may have missed one of the minus signs. Yeah, no, I need to. Well, I need to go back and make sure I do this properly. It's not of pivotal importance, but I should double check that I do this correctly, because I know that this equals, okay, no, I think I know what the problem is. No, this should be correct. It should be correct. This is minus 1 over r cubed. So if I take the gradient to be the prime one, I get double minus, I get a plus here. So this is actually the correct expression for this one. Yeah, does that answer your question? Excellent. Okay. Any other questions? What is so special about 22nd of November? Pass fail option. Okay. Okay. Let me put it this way. I know this is it. I don't have to do it, or that's typically fine. If if this something is something that would help you guys, I'd be happy to give some information. I'll have to think whether I want to just release the all this information, or whether I'll try to do this more on an individual basis. But 22nd of November, that's fine. That's something that I think, you know, okay, I'll stay a little bit conservative because I need to double check what I can and cannot do. But I'll try to give you some information before the 22nd so that you can decide whether you want to go past it. But yeah. You know, I should be careful with the things that I am or am not allowed to say. But I'll try my best to give you some hint to see whether you want to do a pass fail. Let me put it this way. I have also, well, okay, I'll discuss this off the record. Let me close the recording first.